What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our exploration of logarithmic functions. Today, we are going to focus on graphing logarithmic functions and taking a look at their domain. So, graphing logarithmic functions is going to be very similar in nature to how we graphed exponential functions. And if you watch the previous video, that should make sense because we recognize that logarithmic functions are the inverse of exponential functions. So let's focus on how we find transformations of logarithmic functions first. So here we have the vertex form or the generic form for a logarithmic function. Notice that our base b that we saw with exponential functions is listed here, and it is that subscript of the logarithm. So this is the growth and decay rate. So it's still the same component that we had with exponential functions, but it's going to affect the graph a little bit differently. Now we do have other transformations. H is our horizontal shift, which in this format we are going to apply first. A is our vertical dilation, and also can be a vertical reflection if it is negative. And K, sorry, I'm not sure why the graph keeps doing that, but K is our vertical shift. Now we may see horizontal shifts, or sorry, a horizontal reflection. A horizontal reflection would come by placing a negative in front of the X there. We may also have the possibility of having a horizontal dilation, and that would occur by putting a coefficient in front of X inside the parentheses. In Algebra 2, we are not going to focus on those two things very frequently, but just know that those things can exist with logarithms. So in problem number 6, it says to identify transformations, then graph each of the following functions. List the domain and range. Now we did take a look at a graph of a logarithmic function in the first video. And the graph that we actually looked at was log base 2 of x. Now this function does not have any transformations. So as we saw with exponential functions, all exponential functions have a horizontal asymptote. Now all logarithmic functions are going to have a vertical asymptote. The horizontal shifts are going to move that vertical asymptote from the y-axis. In this case, we do not have any horizontal shifts, so our vertical asymptote is at x equals 0. All logarithmic functions have an initial point at 1, 0, at least all the ones that we are going to see. So all of these have a point at 1, 0. If you put in the 1 for x for any logarithm, the output would be 0, as this would become the input of an output of an exponential function. So from 0, 1 on an exponential function to 1, 0. Now, transformations may move that point. We do not have any transformations here, so our first point is at 1, 0. From there, we can use the base, which is 2, to create the new points. So if I were to move up one line, on the y-axis from my initial point here at 1, 0, I'm going to be 2 to the first power units from the asymptote. Now this is a vertical asymptote, so my curve is actually going to take a horizontal path here. So I'm going to be 2 to the first power units from the asymptote, which would be at 2, 1. If I move up another line, I'm going to be 2 to the second power units from the asymptote. And I'm using that 2 as my base. So technically here I'm 2 to the 0 power, and then up a line would be 2 to the first power, and up a line would be 2 to the second power, and we can continue to repeat this pattern. So the next line would be 2 to the third power units from the asymptote, to the right of the asymptote in this case. Now if I wanted to go down from my initial point, this would be 2 to the negative first power units from the asymptote. So 2 to the negative first power is 1/2. So this would be 2 to the negative first power. It's beneath my initial point. Down another line would be 2 to the negative second power, which would be 1/4 units from the asymptote. And we could continue this pattern, realizing that we are going to get closer and closer and closer to the asymptote as we work our way down here. So we can sketch in the curve through these points to represent our logarithmic function. So again, this function is the inverse of the exponential function, y equals 2 to the x power. Thus, it would be a reflection across the x-axis of y equals 2 to the x power. And so here we have our function. Now we also need to give the domain and the range of this function. The domain would be any x values that this function is going to have as part of the function. In this case, we can see that this function goes to the right forever. So the domain would be x greater than 0. So it's not going to intersect 0. It's not going to be on the left of 0, but it is going to go for right forever. So x is greater than 0. The range for this function, we can see that the curve stretches upward and downward. And so the range for this function will hit all real numbers. Now, another way to find these points is to use the graphing calculator. So you could go to y equals and type in the logarithm button. Unfortunately, with what we know right now, we are unable to graph the log base 2 because our calculator gives us log base 10. Eventually, we'll find a way to graph log base 2. But for right now, this calculator is not going to give us the points for this graph. It will give us the points for the graph in B because the natural logarithm is part of our calculator. So I'm going to go ahead and type in the natural logarithm. So negative natural log of x minus 1. And we're going to take a look at the second graph that we should have here. This is what our graph should look like. Now, there is a vertical asymptote here that's not shown on the calculator, but where this graph appears to end, that's actually the graph getting closer and closer and closer to that vertical asymptote. How we can find this based on our directions is to first identify transformations. So we may notice that there is a horizontal shift. This has a shift to the right 1 unit. Remember, inside the parentheses, our generic form is x minus h. So this is actually a positive one for h, a shift right. It also has a negative in front of the natural log. So this is a vertical reflection. So the shift to the right changes my asymptote. My vertical asymptote is going to be here at x equals 1. So it starts on the y-axis, but is then shifted over 1. Now, my initial point usually begins at 1, 0. However, it's going to be shifted over 1. There is a vertical reflection for this as well. However, the vertical reflection is not going to affect that point since it is on the axis. So I'm going to have this point at 2, 1. From 1, 0 to 2, 1 because we've been shifted to the right 1. Now, to find my other points, I can use the calculator, which I'll come back to, or the fact that the base is E. So if I wanted to find points, this is a vertical reflection. So my graph is going to approach the asymptote as we move up and come away from the asymptote as we move down. So this would be e to the 0 power for that point at, e to the 0 power units from the asymptote for that point at 2, 0. The next line down would be e to the first power. Notice I have e to the first power. Notice I have a positive 1 exponent here, even though I'm moving down, because this has been reflected. This, if we remember, Euler's number is approximately 2.71. So it would be about 3.71 negative 1. And we could continue that pattern, finding e to the second power as I move another line down. Or if I go from my initial point up, e to the negative first power, and so on and so forth. We can also use the table function on our calculator. So what our calculator does here is it gives me an error at 1. And that makes sense because we have the vertical asymptote at 1. So there's some points in between 1 and this initial point that we want to sketch. We'll come back to that. We have the point 2, 0. if I go a little bit further, I could start plotting these points. So 3, negative 0.693. I could plot 4, negative 1.09. I could plot 5, negative 1.38. These are not going to be the points that I showed using the base. However, these points will give us the graph of the exponential function. So I'm going to go a little bit further over to the right. I'm going to go down over to 9. I have my first point here. And then I'm going to go to 9, negative 2.07, just to kind of get a point further along here that's going to allow me to draw my curve. Now again, if I wanted another point as I approach the asymptote, it would be E, Euler's number, to the negative first power units away from the asymptote. So about 3.7 units from the asymptote. So we'd be very near the asymptote there. So we can use the base of the function as a distance from the asymptote to create points. And we can also use the graphing calculator to help us create points. Either way, we should be able to draw a sketch where this approaches the horizontal or the vertical asymptote as we move to the left and is working its way away from the vertical asymptote as we move to the right. Now the domain for this function is going to be anything to the right of the asymptote. So any value where x is greater than 1. The range for this function is going to be all real numbers because this function still goes up and down forever. Let's take a look at one more graph here. So here we have a log base 2, which we're not going to be able to type into our calculator. So let's work through how to find this using transformations. So the positive 8 inside the parentheses is a shift to the left 8 units. We do have a vertical dilation, vertical stretch by that a, that coefficient, so vertical stretch by 3. We have a vertical shift, in this case, that negative 1 at the end of the function, a shift down 1. So my vertical asymptote is going to be at negative 8. X equals negative 8 because we have that shift to the left 8. Now, if I had my initial point, it would begin at 0, 1, or sorry, excuse me, 1, 0. It would shift to the left 8 and then be vertically stretched by 3. However, this is on the x-axis, so the vertical stretch is not going to affect this point. Vertical stretch, in this case, would triple the distance from the x-axis. It is going to shift down 1. So this would be at the location, negative 7, negative 1. Now, my graph here has a base of 2, and it has not been reflected, so it's going to take a path that looks like this of some kind. We need to plot some other points. So what we're going to do is move from the initial point to find our new points. Now, prior to this, I would move up 1 and use my base 2 to the first power distance from the asymptote. And then I'd move up 1 more and 2 to the second power, and so on and so forth. For this graph, everything is stretched vertically by a factor of 3. So instead of moving up 1 to be 2 to the first power units from the asymptote, I'm going to move up 3 lines. So each time I increase the power or the base by an exponent and take that unit from the asymptote, it is 3 lines above my initial point or the previous point. So if I go up 3 lines from y equals negative 1 to y equals 2, my point is going to be 2 to the first power units from the asymptote, which is 2 units. I'm going to move up 3 more lines to y equals 5. And I am 2 to the second power unit from the asymptote, or 4 lines. I could move up 3 more spots to y equals 8, and this would be 2 to the third power units from the asymptote. And so here I have some points for my logarithm. Now I want a point headed back in the direction of the asymptote as I move downward. So if I move down 3 lines, that would be 2 to the negative first power units from the asymptote, or 1/2. If I move down 3 more lines to y equals -7, I would be 2 to the negative second power units from my asymptote, or 1/4. And here we see the curve starting to take form for my logarithm. So as I sketch this curve, I can sketch through those points that I have plotted, and we see this logarithmic graph taking form. And it would continue as we work down, approaching the asymptote, and continue as we work up, moving away from the asymptote. So this would be a good graph for our logarithm that was given by f of x. Now, if I want to find domain and range, the domain in this case is going to be x greater than -8. So from my horizontal asymptote, I am working to the right forever. So any x value greater than -8 will be part of my asymptote, or part of my domain. My range is going to be all real numbers. So this graph is going up and it's going down forever. So this is how we can graph functions using transformations and powers, or multiples, powers of the base to find distances from the asymptote. Now, we also focus on the domain of logarithmic functions. So what you may notice in the first equation, x was greater than -8. Sorry, in the third equation. In the second equation, for our domain, x was greater than +1. For our first equation in the domain, x was greater than 0. We can get the domain of any function without doing any graphing by taking a look at the horizontal shifts. The input for a logarithmic function has to be a positive number. And that coincides with the output of an exponential function when we start to take a look at input and output values. But what we're looking for is inside the parentheses, x minus h has to be greater than 0. We cannot have a negative value input into a logarithm. So in problem 7, it says, without graphing, determine the domain of each of the following functions. Well, all I have to do is focus on the input expression for the logarithm. This expression must be greater than 0. So in order to solve this expression for x, I can subtract 3 and then divide by 2. And so now I have the domain for my function. The domain for p of x has to be greater than greater than -3/2. So why -3/2? Well, in this case, we have a horizontal shift left 3 and a horizontal dilation of 2. So that's going to move it left 3, then cut that distance in half. And so this would be -1.5 or -3/2. Let's take a look at another example here, which actually incorporates some new ideas. So again, when I look at problem B, I'm going to be looking at the input of the logarithm, which is x squared minus 2x. And I need this value to be greater than 0. Now, what we could do is we could solve by, or attempt to solve by factoring out the x. We'd have x times x minus 2 is greater than 0. So x and x minus 2 are both going to have some relationship with 0. Or x is going to have a relationship with 0 and a relationship with 2, as we would have x minus 2, and you could solve to get x equals +2, or an inequality with +2. Really what we need to consider here is that we're dealing with a quadratic expression that is put inside of this logarithm. So this quadratic expression, we may realize, would have intersections, as we can see the factors, at x equals 0 and x equals 2. So what we're looking for is the area in which this quadratic function is greater than 0, or where it's above the x-axis. And so we can see this here. It's above the x-axis to the left of 0, so where x is less than 0, and to the right of 2, where x is greater than 2. So our domain here would be x is less than 0, or x is greater than 2. So in this case, because we have a nonlinear function, we have to consider the expression that's inside that input for the logarithm and how that relates to being greater than 0. Take a look at another example that gives us a kind of an oddball or a different scenario, and this would be part C, where we have the log base 10 of 3 minus x over x plus 3. Now, this is log base 10, so this we can, based on what we know now, we can graph this in the graphing calculator. But let's do this without the graphing calculator first. So the input of the logarithm, 3 minus x over x plus 3, does have to be greater than 0. Now, this is a fraction, so let me create a different scenario. A over b has to be greater than 0. Well, let's say a is a positive number. A is positive. In order for the entire fraction to be positive, b would also need to be positive. So I would need a to be positive and b to be positive. If I had a that is negative or positive and b that's negative, you can see my fraction would be less than 0. Now, let's say I had a is less than 0. So there's a negative there with a. Then b would also have to be less than 0. If I put a negative with a and b, the negatives would become positives. So I have two scenarios here where I have to, because I have a fraction, I have two scenarios where I have to essentially consider. I need to consider when 3 minus x is greater than 0 and x plus 3 is greater than 0. And then I would also need to consider when 3 minus x is less than 0 and x plus 3 is less than 0. Now let's solve each of these inequalities. So for 3 minus x is less than 0, I would add the x to both sides and get 3 is greater than x, which is also the same as x is less than 3. And I would have x plus 3 is greater than 0. I would subtract 3 from both sides to get x is greater than negative 3. So what I get is a single inequality here, a compound inequality, where x is greater than negative 3 and less than 3. And this does make sense. Now let's let's take into consideration the other case where the numerator is negative and the denominator must also then be negative. If this were the case, I would add x, so I would get 3 is less than x, or x is greater than 3, and I would subtract 3 and get x is less than negative 3. And this cannot happen. You can't have a number that's greater than 3 and at the same time less than negative 3. So our only case that gives us a domain here would be the first case. So the domain for x would be between negative 3 and 3. Now again, because this has a log base 10, I can check this on my graphing calculator. So log base 10 of 3 minus x over x plus 3, if I graph this, I can see that the function is between negative 3 and positive 3. One more odd case where I take a look at D here, we have the natural log of an absolute value. So the input of the logarithm, in this case the natural logarithm, is x minus 2. Or the absolute value of x minus 2. So if I get rid of the absolute value, then I need to check two scenarios here. X minus 2, the absolute value of x minus 2 has to be greater than 0. But if I want to remove the absolute value, x minus 2 has to be greater than 0. And x minus 2 also has to be x minus 2 has to be less than the opposite of 0. In most cases, we would switch the sign of the integer on the other side of the inequality. But because 0 does not have a sign, x minus 2 has to be greater than 0, and x minus 2 is less than 0. So in this case, we would get that x is greater than 2, and x is less than 2. Sorry. I put an and. These should be ors. They should be or statements. X is greater than 2, or x is less than 2 would be our domain here. So what we would get is that x is equal to all real numbers except for 2. Any number less than 2 or greater than 2 is any number but 2. And this is a natural log, so we can check that one in the calculator as well. So I have that function typed in there. Let's go ahead and take a look at its graph. And so if I look at the graph here, it actually appears that this function hits all of the numbers. But if I go ahead and take a look at the table, where x is 2, I see that there is no value. And then for every other value, there is. So what we have to do in order to find the domain of a function is to take the input value and set that greater than 0. and then solve for the variable. In some cases, when we have quadratics, rational functions, and other types like absolute value functions, we have to take in some extra considerations in the process of solving. This covers basically everything that we're going to talk about in Algebra 2 about graphing logarithms and their domains. So this is a good place to stop. As always, thank you guys for tuning in, and I'll see you soon.